Welcome to the Discrete Universe podcast. Today, especially for you physics-minded listeners, we're diving deep into, well, a really compelling question at the forefront of modern physics. How can quantum geometry dynamics, or QGD, possibly explain the fascinating observations we're making at particle colliders, particularly, the LHC? We've got quite a bit to get through today, ranging from some fundamental challenges in physics right up to the core axioms of QGD itself. Our mission really is to unpack how this relatively new framework attempts to account for all that high-energy stuff we see in these experiments, prepare for an exploration that might just challenge some conventional ideas. Okay, let's unpack this.
Yeah, and to really get what QGD is trying to do, it's useful to maybe think back to Hilbert's sixth problem, early 1900s. He was essentially calling for physics to be treated axiomatically, like geometry. Build it from the ground up on clear, solid principles. QGD, well, in many ways, it sees itself as an answer to that call, trying to provide that axiomatic foundation.
Right. So it's not just fiddling with the existing models. It's proposing a whole new bedrock. But I guess getting a view that different accepted must be, well, a real uphill battle in physics. I think Planck said something about this.
Exactly. Planck made that very sharp observation. New ideas often take hold not because the old guard is convinced, but because, well, they eventually retire or pass on. And the new generation comes in without those same ingrained assumptions. It really speaks to the inertia you find when faced with really radical ideas.
So it sets a really high bar then, doesn't it?
Yeah.
Any new theory can't just, explain one niche thing. It has to match everything we already know and then do more.
Absolutely. There are several major hurdles. First, you absolutely have to reproduce all the successes of the theories you want to replace. That's non-negotiable. Second, you need to offer, ideally, better explanations for things the current theories struggle with, mysteries, anomalies. And third, crucially, you need to make new testable predictions, things we can actually go and check experimentally.
Okay, so QGD needs to put its money where its mouth is, basically. Make predictions we could test, especially places like the LHC.
Precisely. And, as Bernstein pointed out, these things take time. A genuinely new framework needs space to be explored, developed, refined. It's not an overnight swap for theories developed over decades or centuries.
Okay, so QGD has this big ambition, a high bar to clear. Yeah. Let's get into the core ideas then. What's fundamental to this QGD view? I know space itself is a big departure.
It really is. One of the most fundamental postulates of QGD is that space is discrete. Don't think of it as a smooth background. Imagine it's made of these basic units called preons. And they aren't in space, they are space. The dimensions we see, like length, width, height, they emerge from a repulsive force between these preons. It's called Nm gravity.
Wow, okay, so space isn't the stage. It's made of actors pushing each other apart. Dimensions are emergent. That's quite something.
Yeah.
What about matter, then? What's stuff made of in this picture?
Matter is made of the other fundamental entity, preons plus. Unlike the space-making preons, these preons plus are bound together by an attractive force, p gravity. And a key idea here is that these preons plus are eternal. Their total number is fixed, finite, a fundamental conservation law right at the bottom.
So all the particles we see smashing together at the LHC, electrons, quarks, everything, they're just different arrangements of these preons plus, held by p gravity.
That's the core idea, yes. They're the building blocks. All the complexity emerges from how they interact via p gravity.
You also mentioned strict causality earlier. How does that fit in?
Right. Strict causality is another cornerstone. It basically says at this fundamental QGD level, everything has a definite cause. The universe unfolds deterministically, which is, quite different from the usual quantum mechanical picture with its inherent probabilities.
Interesting. No fundamental randomness deep down. Okay, but if space is fundamentally discrete, made of these preons, how do we get the smooth, continuous Euclidean space that works so well for, well, most physics?
Yes. QGD includes a theorem about that, the emergence of Euclidean space. Essentially, when you look at large enough collections of these preons, their individual discreteness averages out. The resulting structure looks, for all practical purposes, like smooth, continuous space. So continuous math works as a great approximation, but it is an approximation.
Like a high-res digital photo looking smooth from afar, but it's still pixels up close. Got it. What about time? That's always a tricky one.
In QGD, time isn't treated like a physical dimension, not like the emergent spatial ones. It's seen as relational. Clocks, fundamentally, are just devices counting recurrences, cycles of some physical system. So when we talk about time dilation clocks slowing down at high speed or in gravity wells, QGD says it's not time itself stretching. It's the actual physical mechanism of the clock, the preonic interactions making it tick, that are slowing down due to those conditions.
The clock's internals are affected, not time itself. That's a very different way to think about it. And how does QGD define things like mass, energy, momentum?
It offers quite distinct definitions. Mass is simply the count of preons, plus, in an object. Very direct. Energy is then proportional to mass, EMMC, where C relates to light speed. And then there's intrinsic velocity. It's momentum divided by mass, VPM. The really key thing here is that QGD claims this velocity is frame-independent, an inherent property, not relative to an observer.
Frame-independent velocity,
Yeah.
okay, and charges. Electric charge, for instance.
Charges aren't seen as intrinsic properties, like this particle has charge. Instead, they're described as disturbances or distortions in the overall preonic field, the environment of both preons plus and preons. And this view actually leads to a potentially testable prediction.
Oh, what's that?
That electromagnetic attraction and repulsion might not be perfectly symmetrical between different particle types, a subtle difference, maybe, but potentially measurable, a deviation from classical electrodynamics.
Okay, so discrete space, preons plus, preons, p-gravity, and gravity, relational time. How does this framework start to explain what's happening in these incredibly energetic collisions at the LHC? I mean, the standard model works incredibly well there.
Right. This is where QGD offers a really different perspective on forces at tiny distances. It proposes that as you get down close to the fundamental preon scale, P gravity, the attraction between preons plus, becomes immensely strong, much stronger than at larger scales, and it actually overcomes the repulsive in gravity between the preons, making up space at those distances.
Wait, so gravity becomes the dominant force down there. That completely flips the usual hierarchy where gravity is the weakest force at the particle level.
Exactly. And this super strong, short-range P gravity is proposed as the mechanism holding atomic nuclei together. It overcomes the electric repulsion between protons. So it's offering a gravitational explanation for what we usually call the strong nuclear force.
Gravity binding the nucleus. That's a radical idea.
Yeah.
So when we slam particles together at the LHC, are we essentially overpowering this short-range supergravity?
In essence, yes. The huge momentum we give particles allows their constituent preon, plus clumps, to overcome that intense P gravity attraction. That allows for fragmentation, rearrangement, which we then see as the spray of new particles in the detector.
Okay, and what about nuclear stability? Why are some nuclei stable and others radioactive?
QGD links that to the balance between the attractive P gravity and the electromagnetic repulsion inside the nucleus. If the protons get too far apart, on average, repulsion can win, leading to instability, decay. And it suggests that emitting neutral particles, like neutrons or neutrinos in decay, helps the remaining nucleus find a new, more stable balance between these forces.
So drilling down in the QGD picture, when particles interact at the LHC, what's actually happening? Is it still exchanging force carriers like photons or gluons?
It's viewed differently. Momentum transfer happens through direct interactions, primarily involving the preons that constitute space. Electromagnetic effects, like charged particles attracting or repelling, are seen as absorbing or emitting polarized preons plus from the background field. But the fundamental dynamics are governed by P gravity holding matter together and in-gravity structuring space. The particles we see are just emergent bound states of preons plus, and their interactions reflect those underlying preon dynamics.
That really is a fundamentally different visualization of a collision. Okay, but for QGD to gain traction, it needs those testable predictions we talked about. Are there specific things QGD predicts that we could potentially look for at the LHC?
Well, we mentioned the potential asymmetry in electromagnetic forces. Finding that would be significant support. Another possibility is making very precise comparisons between momentum transferred electromagnetically versus gravitationally, maybe under specific conditions. QGD's different view of charge and gravity might lead to subtle differences there. And maybe, just maybe, the discrete nature of space itself or the specifics of how P gravity works at ultra-short range could lead to unique signatures in high-energy scattering patterns, or maybe influence the properties of any new heavy particles discovered. But
that requires more detailed theoretical work within QGD to make precise quantitative predictions.
Exactly. That's the next step. Turning these qualitative ideas into hard numbers that experimentalists can actually test against the standard model.
Right. It's a huge undertaking. How does this all look through the lens of Occam's razor? The idea that simpler explanations are generally better?
That's a really interesting angle. QGD, with just two fundamental particles, preons, plus and preons, and two fundamental forces, P gravity and N gravity, certainly looks simpler on paper, doesn't it? Compared to the standard model's roster of quarks, leptons, gauge bosons, Higgs.
Fewer moving parts at the absolute base level, yeah.
But, and this is a big but, simplicity isn't everything in science. Parsimony is good, but explanatory power and consistency with data are paramount. QGD might start simple, but it faces the enormous task of showing it can actually reproduce all the successes of the standard model and general relativity across all scales. That's the real challenge.
So fewer initial assumptions is appealing, but it still has to build the same or better explanatory structure. What are the biggest challenges and, I guess, future directions for QGD then?
Well, as we've touched on, the biggest challenge is demonstrating that it can quantitatively reproduce known physics. That means a lot more mathematical development. And then generating those specific testable predictions, especially for high-energy regimes like the LHC, things that clearly differ from standard model expectations. It's a long road. New scientific ideas need time, they need intense scrutiny, they need development before we can really judge their merit.
Okay, here's where it gets really interesting. QGD paints this radically different picture, doesn't it? Discrete space.
Yeah.
Matter from just preons, plus, unified by these two core forces. Trying to build physics from axioms.
It's a fundamentally different approach. And exactly how it accounts for the whole zoo of particles and interactions we see at the LHC, well, that's still a work in progress. It needs more detailed theoretical mapping to the experimental results.
Definitely. But the core ideas themselves, discrete space, the preons, time is relational, they offer a completely new lens, a new way to maybe interpret these high-energy results and potentially find deeper truths.
So what does this all mean for us? I think it means the search for the fundamental nature of reality is definitely not over. Far from it. Frameworks like QGD, even if ultimately incorrect in parts, push us to think differently, explore new avenues.
And for you listening right now, here's something to chew on. If space, if time, aren't smooth and continuous, but are fundamentally discrete, pixelated at the very bottom, how does that change everything? How does that alter our understanding of the particles that fly out of collisions, the forces holding things together? It's a pretty provocative thought to carry with you as you continue your own exploration of our, perhaps, discrete universe.